This is section 2.2 on polynomial functions of higher degree. So a polynomial function we've looked at is the quadratic function x squared. We are going to be looking at x to the third, x to the fourth, x to the fifth, and so on, and determining what those different functions look like. So to start off, we're going to start off with the definition of a polynomial function. What makes something a polynomial? There are two conditions that a function has to be in order for it to be a polynomial. So the first condition is that it has to be continuous. There can't be any breaks, holes, or gaps in our graph. So if we think about a continuous function, if we were to put our pencil on the graph, we could draw this function without having to pick up our pencil because there's no breaks, there's no holes. The second part of this is that it needs to have smooth and rounded turns. So let's think of the absolute value function. It's shaped like a V. That would not be a smooth and rounded turn. It has a very sharp edge to it. And a polynomial function is going to have a nice smooth turn. Like if we think of the quadratic, that U shape, that would be a smooth or rounded turn. Now, we also have a letter that we use in polynomials. And so this letter is n. And n is used to represent the leading coefficient's exponent or our largest exponent. So n is used to represent the largest exponent. And that letter n will determine what kind of polynomial function we have. So here we have four different polynomial functions. And I'm going to graph out what they look like. So first, starting off, we have the cubic function, x to the third. So 3 here, our biggest exponent in this function, would be considered our n. And so this function looks like this. And as you can see, one side goes up and one side goes down. Like I mentioned in class, it kind of looks like the Disco Man. One arm up, one arm down. Then we come over here to x to the fourth. So 4 would be considered our n in this equation because it is our biggest exponent by default. There are no other exponents in our function. And this graph kind of looks like a parabola, but it's slightly closer to the y-axis. Then we have x to the fifth, which looks like this. These are just rough sketches. Kind of looks like our x to the third function, but just a little bit closer to the y-axis. Then we have x to the sixth, which kind of also looks like a parabola, but even closer to the y-axis than x to the fourth was. So if you take a look at these graphs, you might start to notice the pattern. So what do you notice about the end behavior of even functions versus the odd functions? So when I talk about even versus odd, I'm talking about even exponents, so 4 and 6, versus odd exponents, 3 and 5. Or we could talk about even n's and odd n's because n represents the largest exponent. So take a minute to think about that. So while you were thinking, you might have noticed that even n, the arrows go in the same direction. So here, both up, but if you have an odd n, the arrows go in opposite direction. So one side goes up and one goes down. So that is telling us about what we call the end behavior of our polynomial functions. So what are the ends of our functions doing? What are the arrows doing? Which direction are they pointing? And so that is all going to be based off of the leading coefficient. So now you may have heard this term before in Algebra 2, leading coefficient. The leading coefficient is the number in front of the variable with the biggest exponent. So that is the number in front of the variable with the biggest exponent. And so we call the leading coefficient A. So just like we call the biggest exponent n, we call the leading coefficient a. So I'm going to put in parentheses n. So the leading coefficient is going to tell us about our end behavior. Which way are our arrows pointing? So when the leading coefficient has an odd degree, so this means that n is odd, the biggest exponent is odd. That means that if we have a positive a, so positive a, our function goes down, then up. So that means our arrows first point down on the left and up on the right. If our a is negative, so negative a, that means we go up on the left and then down on the right. So once again, if our biggest exponent is odd and the number in front of that x is positive, we go down on the left and up on the right, as you can see here. Down on the left, up on the right. If it is negative, it's going to switch. So it'll go up on the left and down on the right. Now, when the leading coefficient has an even degree, so an even degree would be an even n or an even biggest exponent. If we have positive a, like our examples at the top, both sides go up. So left and right are facing up. If we have a negative a, both sides go down. So once again, if you have your biggest exponent is even, the number in front of your x is positive, both sides go up, as you can see here. If it is negative, both sides will flip and go down. So now let's talk about what is a zero of a function. So we've kind of talked about this in class. Zero is another word for x-intercepts. So where our graph crosses the x-axis. And so our degree, or n, or our biggest exponent, tells us something about zeros of a function. So at most, our function could have n minus 1 turning points. So if you think about turning points, those are relative maximums and minimums. Our function also has, at most, n real zeros. So it doesn't mean that it has that number of zeros, but at most, it could have that many zeros. So here, for x to the third, this function could have at most 3 zeros. Will it have all 3? Maybe, but not always. So now let's talk about repeated zeros. When will we have a repeated zero? So a repeated zero is if you factor out in, let's say you're factoring out a quadratic, and you get something that looks like this. X plus 2 times x plus 2. So x-intercepts that appear more than once algebraically. So x equals negative 2 appears twice. So that means we have a repeated zero. So the number of times that a zero appears, so this would be twice, if it appears an even number of times, that's going to tell us something about how it looks on the graph. So if you have a zero that shows up twice, like here, what that means for your graph is that it is going to touch the graph or touch the x-axis and bounce off. So an even number of times, so 2, 4, 6, it'll touch the x-axis and bounce. So I'm going to draw a sketch of what that'll look like. So here, I touch the x-axis and I bounce back up. So this would be an even number of times. So something like this, where it shows up 2 times. Now, if it shows up an odd number of times, so that would include 1. If you have a zero that shows up once, so an odd number of times, is going to touch the x-axis and cross it. So it's going to cross to the other side. So what will that look like? That'll look something like this. So let's take, for example, this 0 right here. So this 0, we touch it and we cross. This one touches and bounces. So this is if it shows up an odd number of times. So if you have a 0 that shows up once, this is what it's going to look like on a graph. It's going to actually cross it. And lastly, we have the intermediate value theorem, which is a theorem that is used to determine the existence of zeros. Will a 0 exist? So used to determine the existence of real zeros of a function. So for this, I'm going to write out the mathematical definition. So if there is a value where f of x is negative, so we have a negative y, and a value of f of x that is positive. So we have a negative y and we have a positive y. You can conclude that there is a 0 between those points. So this sounds confusing anytime we talk about mathematical definitions of things. It always sounds more confusing than it is. What this is saying is if we have a negative y value, so I'm going to say, let's say we have a negative y value. So here's -1. Let's say we have a point here. And then let's say we have a positive y value. So positive 1's here, we'll put a point here. You can conclude that there is a 0 between these points. Well, why could we conclude that? Well, in order to connect these, if we're going from negative to positive, we have to cross the x-axis no matter what. So that's basically all the intermediate value theorem is saying. It's kind of stating the obvious. If we're on the negative side of the x-axis and then we go to the positive side, we're going to have to cross over it in order to connect our graph. And since polynomials are continuous, we know that it would have to go through here.